All right. Hello, everybody. So today we're going to start looking at probability. So if you dug through the available file and whatnot, you probably found the script, the bare bones statistics. And the bare bones statistics, uh, at this point, it has 5 chapters in it, and those are the very basic chapters we're going to be covering. After that, I'm hoping to expand a lot more into decision making and a lot more into how we deal with statistics in real world. But before that, we need to cover a couple basics. The couple basics we're going to be covering in this section is just the concept of probability. What you see on the screen, maybe quick announcement there. What you see on the screen is two things. Up here, you see a yellow number. This number refers to how many questions from you guys I managed to solve. There will be announcement on it on the website we use for class. So this is this, and we can deal with that. Down here, you see my expected day where I'm gonna be doing the next either chapter or an answer session. So there is kind of a heads up of when can you expect more to be uploaded. I will be doing little things in between, but this by that time or by that day I should be streaming something or uploading something that is big enough for to be worth noting. Anything else will show up on the screen as necessary. So, chapter 1. And chapter 1 is probability. In chapter 1, we're going to be looking at the basis for decision making. So probability is the basis for it. And again, the concept of decision making or the basis for decision making is based on this kind of concept that low probability means low chance of happening, whatever that's supposed to be, right? Low probability of rain means there's a low chance of rain happening. And what we look at it is we not only use the term probability, but we also use the term how rare things are or how unusual or usual they are. This will become very essential in chapter 2, but for now, right, this is kind of concept-based approach. But if we are going to talk about concepts, we should consider vocabulary. And here comes the somewhat tedious part. Again, if you guys have the script available in front of you, those definitions are there and you can skip a couple minutes. If not, you're just joining us or you are not in my class and you just stumbled upon this channel. Well, hang on, let's do it. So we have vocabulary. So what do we do? Well, first thing we should probably talk about is something called an event. We define an event as a collection of outcomes. Well, outcomes of what, right? Well, we have to specify. In this case, let's call it a procedure. Collection of outcomes of a procedure. Okay, next question is, what is an outcome? Well, an outcome is the result of a single trial, right? trial of what? Well, we tested something, right? We ran some kind of a experiment. Well, what kind of it? Well, we're talking about probability, so a trial of a probability experiment. So that's the very basics. All right. Well, let's expand. If we are talking about a collection of outcomes, that is a lot of things. That could be getting out of the bed with your left foot first, having a black cat run in front of you, having an Uber driver that doesn't know how to use Google Maps, getting divorced, and by the time the day is over, like, well, what are the chances this was the worst day ever? Well, we had this event, worst day ever. But this worst day ever was made out of single outcomes. Well, we have a term for that, and that's a simple event. Now, a simple event is a single outcome. One thing that we had a chance at getting out of the bed with left or right foot kind of thing. So that's this. All right, so next thing is, well, how many of those single outcomes can we have? How many of those simple events can we have? Well, how about we look at all simple events? Well, if we have all simple events, we create this space that holds all of them, and we call it the sample space. So sample space is defined as all simple events. This is this object which contains all the outcomes that we could have, right? All the single outcomes we could have thought about. All right, so this is the very basic. Now, let's look at how we talk about it. So if we look at an example, and let's look at something easy, like flipping a coin. Well, what can we get out of it? Well, you flip a coin, you get some heads or some tails, right? And this is the way we understand it in English. But if we were to make it a bit more systematic, we would have a procedure, right, which would result in a set of outcomes, so some event, right, and we would have all the possibilities as a sample space. So what would be the procedure? The procedure would be, to flip a coin. What would be an event? Well, event cannot be heads or tails. We have to pick one. Now I'm gonna pick heads. So we get a head on the coin flip. So what's my sample space? Well, if my sample space is all the possibilities, well, then it could be either heads, right, or tails. Now we don't write or, we just put a comma and then tail, and then curly brackets. Simple enough. All right, let's try something fancier. Let's say we want to roll a die. And I know for some of you who have been playing D&D for too long, let's not get excited. This is a 6-sided dice. So we have a 6-sided die, we're going to roll it. What's a possible event of this? Well, a possible event of this could be a 2. You could roll a 2. And what would be a sample space? Well, it would be 1, 2, 3, 4, 5, and 6. Right? All the possible outcomes. All right. Well, let's expand. How about we flip a coin 3 times? Right? The procedure is you take a coin, flip, flip, flip. What can we get? Well, we could get something like a tail, right, and two heads. We could get three tails, we could get, but I'm just gonna say we flipped a tail and two heads. So what is my sample space? Now, if you're really good with kind of putting things together very quickly, building a sample space for 3 binary decisions shouldn't be difficult. But for the rest of us, this becomes very tricky. How do you figure out all the possibilities? Well, for that we can use something called a tree diagram. And a tree diagram looks the following. We look at the first step. And the first step, what are the outcomes of the first flip, right? So this is the first flip. Well, we could get heads or we could get tails. And then we do a second flip. What are the options? Well, we could get heads and we could get tails. Same here. If you got a tail first, you could get heads and you could get tails. Right? So this is the second flip. And then we got a third flip, and third flip is again heads or tails, heads or tails, heads, tails, heads, tails. And that's the third flip. Right? And each one of those intersection is another flip. So flip 1, flip 2, flip 3. So let's take a look at this line. If we go heads, 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 gives us 3 heads. The next one is heads, heads, tails. Then it's heads, tails, heads. Heads, tails, tails. Tail, head, head. Tail, head, tail. Tail, tail, head. And tail, tail, tail. And that would be our sample space. So a tree diagram is an easy way to produce sample spaces. Now, you don't have to do it. You can, if you're, again, good at moving things around in your head, you can very easily build this. The downside, besides scooter gang, the downside of that is you're prone to make mistakes. Right? But a tree diagram is an easy way to avoid some of those. So there's this. Will you be expected to produce those in the future? Yes, for the examples I'm going to be giving you in these videos, but very limited use for it in the homeworks. There might be 1 or 2 problems here and there, but the main idea of it is to understand how we produce this. And after we figure out how we can produce this, then the rest of it is what is important. Again, for me, the value comes from the fact that statistics is understood rather than statistics is memorized. There is no benefit to anybody if you just memorize formula. There is a lot of benefit if you understand how those formulas work and how we get those numbers. All right. So if we are looking at probability, well, what is probability? Probability is the likelihood. By the way, I tend to use shortcuts. Spelling is not my strong suit, so I avoid spelling large words out as much as I can. I promise I passed SATs at some point, but I'm just trying to be, making it easy for myself. Laziness, call it. So probability is the likelihood of an event And again, we know what the event is: occurring. Occurring means happening. So that's the problem. So how do we annotate it? Well, we define probability even shorter, well, by capital P. Capital P stands for probability, and it's going to stand for probability through the rest of this class. And then we have some event. Well, we usually annotate those as A, B, and so on and so forth. So the way we starting to think about it, the way we would think about it in most of the math classes you took, is we would think about it in terms of probability of A. So this is the probability of event A happening. Simple enough. All right. So this should cover the basics. Now, once we have this in this kind of function setup, we can do things with it. We could say that, right? This means probability of A plus probability of B, right? Because this is a number. And once we have it as a number, we can do things we usually are capable of doing, numbers like adding or multiplying or dividing, right? Right. So I suppose we should explain, or I should explain, right, that there are three types of probability that we consider. First type is something called observed probability. Now, depending on what a secondary source you use, if you're using another textbook, somebody else's videos, some notes that you have from another class, this is sometimes called experimental. Probability. And this probability is based on an estimate. Well, estimate of what? This is based on estimates of observations. I suppose there's one more term that people use for this. This is empirical. So, observed probability or empirical probability is probability where you actually did something and you got the answer. I'm assuming most people in this class, if they haven't collected baseball cards or played poker online or fantasy football, they are aware of those sports. How do we get those numbers? How do we know that this poker player has 20% chance of winning the poker tournament, or that this quarterback has this many chances to score this many passes, or this baseball player hits an average of 27%? Well, how do we know? Well, we know this because we've been observing them for a while, and after we have amassed a long list of observations, we can, do some averaging and some calculations, and we can figure it out. And so the actual formula we're going to use for observed or empirical probabilities is that the probability of event A happening is equal to the number of times A occurred divided by the number of times the procedure was repeated. Again, we're thinking about a baseball player. How do we know he hits 27% of the time? Well, we observed him for 100 matches or for 100 pitches, and he hit 27 of them. And there's your percentage. Right. Of course, this leads to certain interesting conclusions. For example, what's the probability of... I'm drawing a blank. Hang on. What's the probability of winning a lottery? Well, you haven't won yesterday, right? We tried it once yesterday, you didn't win. So the probability of winning lottery today is 0. On the other hand, if you got married, right? You got married yesterday. What are the chances you can get married today? Well, if yesterday you started counting, day 1, right? You went to church once, you got married once. Your success of marriage is 100%. Right? So if we have done the procedure only once, or limit number of times, some obscure things will show up. Flipping a coin is one of those. Well, let's see. Let's imagine we flipped a coin. And we flipped it one time. We got, well, that's our procedure, right? We got a head. What's the probability of getting a head? You can pause the video if you want. If you flipped a coin once, you got a head as the outcome, right? How many times did A occur? Once, right? How many times did you repeat the procedure? Once. So this is 1/1, which is 100%. Okay, let's say we flip the coin 2 times. And we get heads and heads. Well, then the probability of getting a head is, again, 2/2, which is 100%. Okay, let's flip it 3rd time. If we flip a coin 3 times and we get heads, heads, tails, what's the probability of getting a head? Well, it's 2 out of 3, so about 66.7%. Right? And again, we know that the coin, a regular coin or a fair coin, should flip heads and tails 50%, and yet this one gives us slightly different answer. And again, it is because we're looking at observed probability. So let's expand this and let's look at type number 2. Type number 2 is referred to as classical, right, or theoretical. And classical or theoretical probability is probability based on chance. So this is probability based on chance. Well, chance of what? Well, of a event occurring. Well, this would be easy if there wasn't one little thing we need to consider. And the thing we need to consider is that each simple event... What was a simple event? Simple event was a single outcome. So, right, so each outcome must, and this is important, have an equal... My handwriting is horrible. Have equal chance of occurring. Right? So again, classical probability refers to a probability that is based on chance of an event occurring. But each simple event, right, each outcome of that procedure must have an equal chance of occurring. And again, we can look at it as a formula, and that's number of ways A could occur divided by number of simple events. Right? So how many ways can A occur? How many different outcomes can we have? Again, if we consider flipping a coin, right? Well, we could have heads, right, or tails in the sample space. So if we ask about the procedure, about the probability of getting a head, well, how many ways can you flip a head on a coin? Once. Out of how many possible events? Well, we could have a heads or tails. So that's 2. So that becomes 50%. It doesn't matter how many times I flip a coin, because each time I'm flipping a coin, I'm picking one of the 2 sides, right? Same with dice. So roll a dice. So what's the probability of getting a 1 on a die? Well, there's one side with 1, right? It's only 1, right? There's only 1 of those. And how many sides are on the dice? 6, right? There's only 1 of those, and there's 6 sides. And so this becomes 1 out of 6. Which comes out to be about 16.7%. Note on calculators. For the final, you might need a calculator, so that would be beneficial. What you're looking for is you're looking for a calculator that has the following function. Has an NPR, NCR, and an exclamation point. This is permutations. This is combinations. This is factorial. Now, most testing centers that I know of will have a calculator for you to borrow or lend. So that's one. On some of the calculators, those functions will be hidden. In case of TI-30, that's hidden under the PRB button. On the TI-83s and the likes, it's hidden under the math menu. And again, don't spend $20 or $30 on a calculator. I buy most of my calculators that I seem to be losing every semester for some reason. I buy them at Goodwill for like $3 or $4. So this. Now, for a lot of the calculations we are doing, one of the links I posted should have some fancy online calculators, so you can at least get through those, and then by the end of the semester in 4 months, you can probably scavenge one from somewhere, at least for a little bit. So that's that. So again, you want a calculator, you want a NPR, NCR, and factorial. Moving on. All right, so this is the observed, and there's the classical. So I said 3 types. Well, then what's the third one? Well, the third one is well, a politician one, I suppose. Third one is called the subjective. And subjective probability doesn't have exactly a formula. It has a definition, and it's an educated guess. That's what it is. So if a doctor tells you, you should get a flu shot because you have 20% of catching the flu, how does he have the 20%? Did he meet you in bunch of parallel universes to have a big enough sample to have observed probabilities? Or did he study you on a molecular level that knows everything about you and knows all the possibilities of catching a flu, all the simple events, and he can do classical? No, he's doing a subjective probability, and he just is estimating to the best of his ability. Now again, experience helps with that, but it's not a good enough driving force. So we have to be very much aware of the where's your data coming from. Is it observed? Is it classical? Is it subjective? Okay. So that being said, let's look at some very basic examples just to get us comfortable. Again, after we write the example out, I'm gonna take a deep breath so you have a time to pause the video and try it yourself. So let's look at the probability of selecting a club from a deck of cards. So reminder, deck of cards. So a deck of cards. A deck of cards has 52 cards, has 2 colors, right, red and black, has 4 suits, and that's hearts, spades, hearts, spades, clubs, and diamonds, and it has 13 different cards per suit. That's 2, 3, 4, 5, 6, 7, 8, 9, and 10, and then Jack, Queen, King, and Ace. So that's a deck of cards. Just a quick reminder. I'm assuming everybody knows, but just in case. On the other hand, if you don't know what a deck of cards looks like, we should meet and we can play poker. I mean, because otherwise I will lose. Apparently, statistics only get you so far in poker. Alright, so probability of selecting a club. Well, that's probability of selecting a club. Is this classical? Is it observed? It is classical because all cards have the same chance of getting picked from a deck, right? Assuming the deck is shuffled. How many clubs are there? There are 13 clubs. How many cards in the deck? 52. So this comes out to be about 1/4, right? Because you're picking 1 out of 4 suits, and that comes out to be about 25%. Easy. Okay. So that's one. So look at this. What's the probability of flipping a tail, right? If after 100 flips you got only 27 tails, right? So you have a coin, you flipped it 100 times, you got only 27 tails. What's the probability of flipping a tail? Well, again, classical, you want to scream 1/2. But because I'm giving you this extra piece of information here, right, that you did the 100 flips, that you got 27, this coin might be weighted. It might not be a fair coin. So when you look at the probability of tail, you have to go back from classical and start looking at observed probability. And observed says how many times did it occur versus how many times did they repeat the procedure. Well, it occurred 27 times. How many times did we repeat the procedure? 100, which means that the probability of flipping a tail is 27%. Okay, super. All right, so let's expand. Let's do one more. So I'm assuming we all love magic, right? So imagine we have a magician. We have a magician that does some trick, So magician does a trick. And let's assume you love magic. I mean, oh, magic, right? And you go see this magician over and over and over and over and over. So, yeah, after seeing, say, 170 shows, right? You realize that the magician only succeeded only 80 times. Right? So a magician does the trick, you see his show 170 times or her show 170 times, and they succeed only 80 times to perform this trick. Well, so what's the probability of a successful trick? Well, it's not classical, right? It's not subjective because we have some numbers, we have some data. So we're looking at observed. Well, observed says we succeeded 80 times and we tried it 170. Well, what is that number? That number comes out to be about 47.1%. Is this the right number? What is the only number we have? And here comes the second question. Is this good number or not? Like, is this good? I recommend you pause the video and try to answer this question. Is this good? Is this good or not? Is this good probability? 5, 4, 3, 2, 1. I'm assuming by now you unpaused the video. Welcome back. This is a question that you are not answering. Is this a good number? Well, it is the only number you have right now. At this point, you only stalked one magician, so this is the only number you have. That's one. Two is 47%. You might say is low, right? He gets it less than half of the time he gets it right, but maybe the trick is extremely difficult, right? So 47 would look good. The same thing we can do about surgeries, right? If you go under a knife in a hospital, you really want your surgeon to have more than 47% of success. Like, you would like to have it at 99, preferably 100, but 99, right? So 47 ain't looking very good. Well, unless it's some very complicated neurosurgery, which most physicians botch, and 47 sounds fantastic, right? In public administration or in most social studies, you're going to end up in kind of a 3-category split. You have the data, you have the decision, right? And you have this middle section where there's overlap. If you're looking just at data, then this is the number. It's great. This is the only thing you have. You're fine with it. If you're looking at the decision part, then you both need data from your current trial or your current set of information, but you also need data from somewhere else to compare it to, right? So the decision if this is good or not very much depends on what do you have access to. At this point, we're going to say that this is the only number we have, so you cannot say if it's good or not. Okay. Let's do one more. So what's the probability of selecting a red jack from a deck of cards, what's the probability of selecting a jack? Well, so it's called red jack. What's that? Well, how many red jacks are there? There's two, right? There's the diamonds and the hearts. So there's two red jacks. How many cards? 52, right? So this comes out to be 1/26. Quick note is that although you can, and in a lot of cases when you use online calculators, you're going to get very precise and long answers. In some cases, leaving it as a fraction is just as good, at least for me, for the purpose of grading, because then I know where you got the information from. I'm fine with this, but I'm also fine with a fraction like this. Unless it's specified, leave it as a fraction or leave it as a percentage. All right. So this is great. Let's do one more. What's the probability of a traffic jam on your street? What's the probability of a traffic jam on your street? Say tomorrow. Do you know? You don't? Well, it depends. If you have a doctor's visit or you need to go to class, I would bet it's like 80%. But if tomorrow you have nothing to do, tomorrow is the start of the long weekend and you don't care, then maybe 0%, right? On the other hand, it's a long weekend, so maybe it's like 45%, right? And we keep on going back and forth. What kind of probability is this? Well, this is a subjective probability, right? This was classical, right? This was observed. This is subjective because you don't know. You don't have the data. You don't have this. So what you do is you make an educated guess and you take it from there. So that's this, right? Let's keep going. All right. Next question. This question is important, and I will grandstand and soapbox at the end of it, but this question is important. So the question goes like this: find the probability that if a couple has 3 kids, 2 will be boys. So, seems like a very obvious question. Now, we're going to make a little assumption. We're going to assume equal chance between boy and girl at birth. It's not exactly, our observed probability for this is not exactly 100. It's not exactly split in the middle 50-50. It's more, there's more girls being born than boys, but for this problem we're just gonna assume half and half. So find the probability that if a couple has 3 kids, 2 will be boys. And we're gonna pause, we're gonna try to do this problem. 5, 4, 3, 2, 1, and let's look at the solution. So I'm assuming by now you looked at it and you thought that maybe it would be better to solve it systematically. Well, we started the chapter with talking about procedure and event. Right, so we have events and procedures. What's the procedure? It's kind of awkward, but having 3 kids is the procedure, and first of all, you cannot talk about having 2 boys when you only have 1 kid. That's just awkward. child snatching and whatnot. On the other hand, this is not a bio class, so I'm not going to explain how we get free kids, but there was a stork involved, some major things were happening, but we got free kids. We finished the procedure and we got free kids. And so what's the event? Well, the event is 2 boys, right? I'm going to let you pause this for a second and think about it. Is this the event? Now, pause over, right? So now this is the grandstanding that I'm going to do. Most people in most of my classes, across most of the teaching I ever done, says the event is 2 boys. So my question is, what's the third kid? A unicorn? So there's 2 boys plus unicorn? Right? Because people just say 2 boys and they forget about the girl, right? It makes the girl, by omission, less significant. And because it makes her less significant, it creates a systematic discrimination against women, or against girls in this case, right? Because we are omitting it, it's not important enough to mention. Everybody assumes it's implied, but that assumption of that it's implied kind of skews your data because you just don't show it, right? So this is a big thing because I've seen it happen in some papers, I've seen it happen in some discussions. It's very easy to forget about the third kid. It's very easy to forget about the third kid, but by forgetting about the third kid, because it's asking only for 2, that third kid becomes less important, and it's not, because you cannot have 3 kids with just 2 boys. I'm going to let this sink in, and I don't want to grandstand for too long, but this is a big thing. Heads up, if question like this ends up on one of the homeworks or the final exam, no mercy. I don't accept this level of discrimination, systematic discrimination. So you have been warned. Now, let's see if we can fix the problem. So we're looking at the event, and that's 2 boys plus 1 girl. Now, we can argue that either the boys or the girls should be mentioned first based on if we are doing by the group size or alphabetically, but that's a conversation for another. Because we're talking about equal chances, we're talking about classical probability. Right, so we have classical probability with this. All right, if we're talking about classical probability, then probability of 2 boys plus 1 girl, right, of this 3 kid monster, right, the probability of that should be the number of ways we can get 2 boys and 1 girl over the total number of ways we can have 3 kids. So how can we have 2 boys and 1 girl? Well, we could draw the tree diagram, or I could just write it out. We could have boy, boy, boy. We could have boy, girl, boy. We could have boy, girl, girl. And we could have girl, girl, girl. What else can we have? We could have boy, boy, girl. You could have girl, boy, girl. You could have girl, boy, boy, and I'm missing one. And you could have girl, girl, boy. And there's our 8 options. And so now the question is, which ones are the ones we're interested in? Well, we are interested in not 2 boys, right? We're no longer interested in just 2 boys. We're interested in 2 boys and 1 girl. 2 boys and 1 girl. No, no, no. 2 boys and a girl. No. 2 boys and a girl. And no. Right? If you just had 2 boys, you might end up counting 3 boys because there's 2 boys in it. But when you specify 2 boys and a girl, this question becomes a lot simpler. And that's 3/8. Which for those of you who are curious, is about 37.5%. Questions? I'm assuming not. Oh wait, I'm talking to myself. All right. So let's. Oh, sorry. Let's just shift it over here. All right. So let's expand. And the expansion we're going to do to that is we're going to talk about this probabilities that we are talking, and probability is always between 0 and 1. It's always between 0 and 1. Probability equal to 0 is an impossible event. It won't happen. On the other hand, probability of 1 is a certain event. I wouldn't say guaranteed because that has certain connotations and might get you in trouble, but saying it's a certain event that it will happen are ways to put it. So probability is always between 0 and 1, and if it's 0, maybe I should go like this, right, between 0 and 1, but if it's 0, we consider the event to be impossible. If you consider the probability of 1, means it will happen. All right. So one last expansion is the law of large numbers. And the law of large numbers says the more a procedure is repeated, the closer observed probability will get to classical. Right? If you remember the coin flipping, right? You flip a coin once, you get heads. The probability of getting heads is 100%. But if you keep on flipping and flipping the coin over and over again, eventually there will be tails, and there will be a lot of tails and a lot of heads. And the more you flip, the more heads and tails there are going to be. Eventually, you're going to get an observed probability that is very close, if not equal to classical probability. So law of large numbers says if you repeat, eventually you're going to get to a classical probability, or at least very close to. Now, last thing that I want to talk about here is I want to talk about gambling. The reason why I want to talk about gambling, because gamblers, degenerate gamblers, have two things that I noticed them talking about. So degenerate gamblers. And they talk about the hot streak and the cold streak. And they talk about hot streaks, right? You play cards and I'm hot right now at this table, or it's a cold table and I'm just not getting any luck. And when they talk about hot streaks, they make an argument, I'm winning, so I should play. I should keep on playing. Right? And if they have a cold streak, right? What do they say? They say, I will play, I keep on playing. Because I will win eventually. Right? And they are actually doing statistics the wrong way. Because when they're on a hot streak, they're thinking about observed probability, right? Observed probability says what? It says if you won 3 out of 3, then the probability of winning is 3 out of 3, which is equal to 100%. Right? Yeah, I'm hot. I won 3 out of 3, which means that I'm going to win the next one. Especially if you play games that are based completely on chance. Roulette, I suppose, is one of those games, or one of those slot machines. When you have a cold streak, on the other hand, you look towards classical. And classical says, right, that what? Well, that if you play enough, law of large numbers will kick in, right? And since gambling would be illegal if you couldn't win, eventually you're gonna win, right? If I have, say, 5% of chance of winning, so for example, if there is 5% chance of winning, right? Then in 20 games, you win once, right? On average. But this is on average, right? So the general gambler is a person that will look at observed probabilities for one and classical probabilities for another side of the same kind of behavior. So don't be a degenerate gambler. All right. So this is this. All right. On the next, should we keep on going? Well, how much do we have? Let's keep going. I'm having fun. Sorry, guys. I talk to myself. This is what happens when you are stuck in front of, 2 beam lights and a microphone, and no one there to stop you. All right, so let's take a look at the next thing. Let's look at complementary events. Let's see if we can find them. Complementary events. Super. Okay, so we are at 1.2.4 if you're following the textbook or the script. So this is 1.2.4. Alright, I'm rocking it. Cool. Alright, so let's talk about complementary events. Complementary events are events, so these are events which are mutually exclusive. Now, mutually exclusive means they cannot happen at the same time. And what do I mean by event? Well, I mean a collection of outcomes. Right? So there's a collection of outcomes, and the complement of that collection of outcomes cannot happen at the same time. So how do we refer to that thing? Well, we refer to it as a complement. You're anything but kind of approach. So a complement, I suppose we need to define it. We define it like this. There's a bar across an annotation for a complement, and we defined this as a complement of A. So that's how it's defined, right? And this is all the outcomes when event A does not happen. So a complement is denoted with a bar across, right? In some cases, in some textbook, it will be defined with a little c on top. And so we read it as a complement of A, and is all the outcomes when event A does not happen. So what happens if we flip a coin, right? And well, what is our event? Well, let's say we define our event as heads. We get a head, right? So A equals head, right? Event A is the head. So what's a complement of A? Well, it's all the outcomes of a coin flip that are not head. Well, coins have only two outcomes, heads and tails. So this is a tail. All right, let's try another one. Let's say we look at an event where we roll a 4. So we have a 6-sided dice, we roll a 4. That's our event, right? So this is our A. So my question is, what's the complement? What's A with a dash across? Well, it's not rolling a 4. What does mean not rolling a 4? Well, it means rolling a 1 or a 2 or a 3 or a 5 or a 6. Right? That's what means not rolling a 4. Means roll everything but 4. Alright. Let's make it a little bit more exciting. Looking at this last example, what's the probability of 4? Well, probability of 4 is there's one side on the dice that has 4 sides, there's 6 sides altogether, 1/6. So what's probability of complement of 4? Well, there are 5 sides on the dice that aren't 4, there's 6 dice altogether, there's 1. Yes. Now, what is exciting out of this very simple example is that the probability of an event plus the probability of the complement must, and I cannot stress this enough, equal to 1, right? Or 100%. Well, why? Well, because we have all the possible, right? If we put all the possible outcomes, so this is the sample space, right? If we designate this little section here as A, then all this other section around it is the complement of A. Right? So together they have to cover the whole sample space. And this is important. The idea of complements is important. Alright, so now that we have this, let's expand. Well, we're going to expand by talking about another types of events, which is compound events. And compound events are compound events. are events which join two or more simple events. Right, so a single compound event is an event that joins two or more simple events. So what would be an example of that? Well, let's say we want to roll 2 dice, right? If you roll 2 dice, what is a possible event of that? Well, a possible event of that would be to roll a 6 and a 2, right? Now, that is. So what would be a simple event? Well, there's 2 simple events. There's a simple event of rolling a 6, and there's a simple event of rolling a 2, right? But this event that combines the fact that you rolled a 6 and the fact that you rolled a 2 is a compound event. All right, so now that we know this, let's look at a specific version of compound events denoted by addition. So addition rule. An addition rule is presented the following way. Probability of A or B. Now we have to get used to the fact that in mathematics or and and have slightly different meanings than in common language. The example I gave in class is my wife asked me if I want steak or fish for dinner. My answer was yes. The reason why it's yes because addition rule means probability of A occurring or probability of B occurring or probability of A and B occurring at the same time, or if we like, in a single trial. Right? So or in mathematics means either A or B or both, which means that in case of the steak and fish example, that means either steak or fish or steak and fish. All right. So we run into a little problem if we decide to split things a little bit. So for example, there's this statistic I found somewhere in a paper that produced the following. College students, male and female, and again I apologize for the heteronormativity of this example, had majors in engineering, and nursing. Right? And there's the table that was given in the paper listed the following numbers. So there were 73 male engineering students, there were 20 male nursing students, there were 17 female engineering students, and 107 female nursing students. There was more females than males. The totals were 93, 124, 90, 127, and 217. So this was a table that summarized observation for 217 students. 93 were male, 124 were female, there were 90 engineers and 127 nurses. That was what the table was given. So what happens if I decide to go probability of male or nurse? If I take a probability of male or nurse, right, and this is a very very specific question I can ask, right? What's the probability of picking somebody out of this 217 that is a male or a nurse? Well, we're gonna look at probability of picking a male. Well, how many males are there? Well, there's 93. Right? Probability, so 93 out of 217. Plus, right? Probability of a nurse. Well, probability of a nurse is 127 over 217. Okay, well, I don't know any better, so I will just go 93 plus 127 divided by 217. So that's and if you followed me along, you're going to get that this is 101%. And we remember that probability between 0 and 1. So what the hell happened? Why are we getting 101%? Well, I followed it, right? One or the other or both? Well, we covered both, right? So let's take a look at what we got. Let's do it slower. So what do I got? Well, if I counted the males, I counted 73, right? Plus 20. Since there's 217 everywhere, I'm just going to make a large big fraction. And then for nursing, we got 20 plus 107. Right? And that's my 93, that's my 127. Anybody notice something really weird about it? Male nursing students got counted twice, right? And so we ran into a problem. We need to get rid of this double count. And the reason why we need to get rid of this double count is that if we have not mutually exclusive, right? Not mutually exclusive. Mutually exclusive means what? Mutually exclusive means that there is no overlap between male and nurses, and there is. So they are not mutually exclusive, right? There we have not mutually exclusive, right? Events, right? We must eliminate double count. And double count is a semi-informal way to look at it. Right. Well, in our case, it was easy. We just took it out 20 and it worked. So it's 73 plus 20 plus 107 divided by 217 and it works. But how do we do it systematically? Okay, well, we can look at probability of A or B. Well, that equals to probability of A plus probability of B, right? And now what is this number, this double count? This is something that has both male and nursing in common. So we need to minus, well, something that has a male, so something that has first category and second category in common. Right? So this is elimination of double count. The important part is that this has to happen at the same time. So this is in a single trial, and that's important, right? So you cannot, if you're looking at or, you're looking at this, and then you remove one of the double counts. So this and, which we're going to see again in the future, this and means at the same time. Right. So what's the way we can look at it? Well, Venn diagrams provide a little bit of an insight. So imagine we have our sample spaces. We can have two ways to look at it. We could have, say, event A over here and an event B over here, or we could have, as we did in the previous example, we could have an event A and event B. Right? In this case, event A and event B do not overlap, so there is no chance of having double count, right? Probability of picking a male or a female, right? Males, females, there is no double count, so we don't worry about this. This is called disjoint events. That's mutually exclusive. In this case, we got this really nice section right here in the middle where those two events are overlapping, and this little section right here is the probability of A and B, and those are not disjoint. So if they are disjoint, probability of A and B equals to 0, which means that this is not an issue. If they are not disjoint, we have to account for this double count that we did here. All right, so so let's look at some examples. So imagine a probability of selecting a heart or a club from a deck of cards. Well, that's probability of a heart or a club from a deck of cards. Well, so that's what equal to what? Well, that's probability of a heart plus probability of a club minus probability of a heart and a club. Probability of picking a heart, well, there's 13 hearts across 52 cards plus probability of a club, still 13 over 52, minus, well, how many are there? How many cards are both a heart and a club? 0, right? And this comes out to 0.5, right? Or 26 over 52, or 50%, right? And this is kind of a classical approach to it. Can we do a real example? Yeah, we could use this table, right? Which we already started here. We could also look at probability of selecting what? Oh, let's say a spade or a queen. Well, this is probability of a spade or a queen, which equals to probability of a spade plus probability of a queen minus probability of a spade and queen. Well, let's see. Again, probability of a spade, well, there's 13 spades over 20 over 52. Plus probability of a queen, there's only 4 queens in the deck, 52. Minus, how many cards have a queen and a spade in them? Well, 1, the queen of spades, right? 52. And that comes out to be 16 over 52. And if you're interested, this is about 30%. Alright, so let's do some theory. The theory we're going to do, let's talk about complementary events. If we have complementary events, what is probability of A or complement of A? I'm gonna give you a second to pause the video and try to sort it out, but let's see. 5, 4, 3, 2, 1. Well, this equals to probability of A plus probability of complement of A, right? Minus probability of A and complement of A at the same time. Well, what is that? Well, that equals to probability of A plus probability of complement of A, because we cannot do, and this. Because they are mutually exclusive, right? Because complements are mutually exclusive, this equals to 0. Which means then we just get probability of one plus probability of the other, which we know equals to 1. So probability of A plus probability of complement of A equals to 1. Which, again, this is a number, this is a number, this is a number, which means we can move things around. Or now one could ask why the hell we want to make 3 equations when we had 1, is because those might be useful. It might be easier to talk about probability of 1 as a function of the whole minus the complement. Means if you know the probability of the complement, you know the probability of the event. If you know the probability of the event, you can get the probability of the complement, and that's useful. No, how do we get it to be useful? Well, imagine the following. Imagine that we know for a fact that probability of having a girl equals to 51.2%. How do you know it's observed? We track how many kids are born, how many of them are girls, and we get this number. So my question is this: what's the probability of a boy? Well, probability of the boy is the following. Probability of boy equals to what? Well, a boy is the opposite of girl, so this is really probability of the complement of being a girl. Which is what? Well, which is 1 minus probability of a girl, which in our case is 1 minus 0.512, which comes out to be 48. Now again, I'm assuming most people could do this very quickly in their heads, but what we would do is we would exactly do this. The reason why we do it slower like this is because this avoids certain mistakes and allows us for a systematic approach to problems. So again, the reminder is that the addition rule is specified the following: probability of A or B equals to probability of A plus probability of B minus probability of A and B in a single trial or at the same time, either one or the other. All right, super. So this is sketch of part of chapter 1, the first part. I will be adding more soon, and hopefully this will supplement all the other things we are doing. Thank you again, and look at our website to find how we can actually interact through me answering your questions while I do this. Thank you.